Now, if you don't have time to do a full surface analysis, if you just are giving a quick glance to a surface map on the morning of a severe weather event, you can identify where a surface low is approximately located by looking for areas where the winds are spiraling counterclockwise around a given center. Winds spiral and rotate counterclockwise around a surface low. In our example here, we can see that is located somewhere there in the far southeast Nebraska, northeast Kansas, northwest Missouri corridor. Notice how the winds over much of eastern Nebraska are out of the north or north-northwest, turning to more westerly winds over eastern Kansas, more southerly flow over northwest Missouri, with more easterly and northeasterly flow over much of southwest Iowa. So at the center of that kind of spiral, that counterclockwise spiral in the winds, is going to be where your surface low is located. Also located near the station with the lowest pressure, which would be this one here, 997.8 millibars. And of course, a full pressure analysis, isobar analysis, will give you the best chance of really pinpointing where that surface low is. But if you don't have time to do so, those are some good tips to help you find where that surface low is. In this example here, it's going to be located at the center of that lowest pressure contour there. So we would mark our surface low with a red L. Next, we're looking for fronts, cold fronts and warm fronts, and any other boundaries that are available at the surface. These boundaries are, again, very critical in the severe weather process because they can help initiate storms. We have our troughs that can help actually prime the environment for storm initiation, and then that forcing along these frontal zones where the winds actually come together, that can provide a little bit more focused forcing to actually initiate the storms themselves and set the severe weather event in motion. With a surface low, there is always going to be a cold front and a warm front. A cold front is usually always on the western or southwestern or south side of the actual surface low. And then the warm front is going to be on the eastern or northeast or southeast side of the surface low. So the cold front is always going to trail the warm front. So first, let's take a look at our cold front. Now, the way we want to find out the position and determine the position of frontal zones is through multiple factors. There are multiple ways that we can actually determine where a frontal zone goes. The first of these is through pressure tongues. When we do this isobar analysis, this pressure analysis at the surface, we can sometimes come up with these pressure tongues, these kind of tongues of the isobars here that kind of stick out, very much like a trough in the mid and upper levels of the atmosphere. It acts kind of like a ski jump. These pressure tongues are areas where the isobars kind of stick out a little bit like this. That is a classic sign of a frontal zone. We also have some evidence of a frontal zone through wind shifts. So for example, if the winds are shifting from, say, westerly across one area to more southerly in another area, a boundary is likely in that location between the westerly winds to the west and the southerly winds to the east, because along frontal zones, the winds converge or come together. Those are really the main two features that can allow you to pinpoint where a frontal zone is located. We also can have temperature and moisture gradients. So if temperatures are very cool on one side of a boundary and very warm on the other side, there's likely a frontal zone there. Also moisture. It can be a lot drier on one side of a boundary and a lot more moist on the other. So let's take a look here at our example. Our surface low is right in here, and so let's take a look at our cold front. Again, it's mostly going to be on the southern side or western side of the surface low. We see right here a nice little pressure tongue right there across eastern Kansas into northeast Oklahoma, down even into central Oklahoma. We also see a nice wind shift. Winds across much of Kansas out of the west or northwest, even down into Oklahoma as well, shifting to more southerly and southwesterly here across far eastern Kansas, Missouri into eastern Oklahoma. So there's a clear wind shift in here, co-located with that pressure tongue. And we also have a temperature and moisture gradient. Temperatures in the 50s and 60s back here to the west, temperatures in the mid to upper 70s here to the east. Also dew points in the 40s and 50s back to the west, with dew points in the 60s off to the east. So with frontal zones, you want to see multiple of those factors we talked about be in place where that frontal zone is located. You don't just want to see one of those factors in place and the rest not be there. You want to have multiple pieces of evidence to tell you where that frontal zone is located. So in this case, for the cold front, we have a very well-defined pressure tongue, very well-defined wind shift, temperature gradient, and moisture gradient. So with confidence, we can put the cold front through that wind shift and through the pressure tongue here, down through eastern Kansas into northern and north central Oklahoma, right in there. And that would be our cold front. Cold fronts are drawn in blue, always connected to the surface low with triangles that are pointed in the direction of motion. For a cold front, cold air is always moving into a region of warmer air, so the triangles would point toward the warmer air mass.
Join our channel membership and unlock extra videos, live group coaching, and unlimited Q&A.
Let's try our warm front. Our warm front is always going to be, again, off to the north or northeast, or generally on the eastern quadrants of the surface low. So once again, we're looking for pressure tongues, moisture gradients, temperature gradients, and wind shifts. So right away, we see a little bit of at least several different pressure tongues in here. So right away, just from looking at the pressure tongues, we can't really pinpoint where the warm front is located. We see a little bit of one right in here, one up in here as well. But this northern one may be the one to look for because we have a very well-defined wind shift. Winds here across northern Missouri out of the south, and then we shift to much more easterly flow. Winds out of the east, southeast to east, northeast here, up into far northern Missouri, southern Iowa. We also have a clear temperature gradient as well. Temperatures shifting from the 70s here across Missouri, central Missouri, to the 50s and 40s up here to the north. Also a moisture gradient, dew points in the mid to upper 60s down here across much of Missouri, dew points in the 40s and 50s off to the north. So it looks like our warm frontal zone is located somewhere in here. Here up to the north may not be the exact one. It might be a little bit farther down to the south here through the southern pressure tongue, because that's where our most robust moisture gradient is. We do see a moisture gradient in both of these pressure tongues here, but the southern one may be the one of note. So the warm front probably is going to go right in here. Now, this is a little bit arbitrary, and it takes a lot of practice, but you'll get the hang of it once you practice a lot with these surface lows and pinpointing these surface lows and frontal zones on surface maps. Warm fronts are denoted by these half circles, again pointing toward the direction of motion. With a warm front, the warm air is going into the region of colder air, so the pips always point toward the cooler air. So that is our basic surface analysis. Why do we need to do this on the day of a severe weather event? Well, these boundaries and the positions of these boundaries can be very critical in telling you where exactly you need to be to target for a storm chase. If you analyze a cold front and that's your initiating boundary for storms, and you analyze it 100 miles off, you're just taking a quick glance, you misanalyze it, that can put you way out of position for being on the right storms. So you really want to get in the habit of really looking at the surface map in detail. You don't have to do this full-blown analysis every single time, but at least looking at your surface map, your raw surface data, finding where those winds spiral around in a counterclockwise fashion. We pinpointed where that was by eyeballing it. The low was somewhere up here in far southeast Nebraska to northeast Kansas. And then your frontal zones, you're again looking for wind shifts, temperature gradients, moisture gradients. We see a clear temperature gradient here, wind shift from more westerly winds to more southerly winds. So there's very likely a cold front somewhere in this vicinity here. Warm front, same thing. We see a very well-defined temperature gradient up in here. And so that is how you would pinpoint those frontal zones and the location of the surface low without actually doing a full surface analysis. Those are your main things that you want to be looking for on the surface map. We also can have other boundaries like dry lines. Dry lines separate hot, dry air to the west from warm, moist air to the east. Dry lines can be very important in severe weather formation, especially on the plains. We can also have outflow boundaries from previous convection, but you're always looking for those clues we talked about. Multiple clues. You want to have temperature gradients, moisture gradients, wind shifts, and if you do a full analysis, those pressure tongues can really help you out in giving you the exact location of where those boundaries are.
Remember to check out those links in the description below, and then watch another video.